Last time we were together, we were trying to find a way to calculate that exact area below a curve, that blue area that I have shaded under the graph of this f of x here. And we were getting at it by using rectangles, those green rectangles that I have drawn. And we ended with this sort of horrible looking expression over here on the right. So let me remind you of what the parts of this are actually calculating. So we were calculating the width and the height of those rectangles. So we were calculating the width, that was our delta x. So this was the width of each one of those rectangles. And that was equal to b minus a over n. So a and b were the endpoints of that interval. We would figure out the width of the interval and then divide it by n, the number of rectangles. In my picture, I've got 4, but we could have as many as we wanted. And then each rectangle, we were calculating the height by using a y coordinate. So this f of xi was the height of an individual rectangle, and then we were adding them up with that summation notation. So that summation notation said, add up all your rectangles. And then I slapped this limit on the front of the sum, and I said, if we could let the number of rectangles tend towards infinity, then we wouldn't be approximating the area anymore. We would be able to calculate the exact area. So this limit out here takes our approximation to an exact value. Okay, so this limit takes our approximation to an exact value. And as ugly as this expression on the right is, it's actually this incredibly important quantity in calculus. In fact, it goes on to give us applications in physics and engineering and probability and statistics and economics and medical research and in space flight and in graphic design and all over the place. This expression over on the right is an incredibly big deal. So this expression is so important and does so many things for us that we're going to give it a special name and a special notation. So we're going to call this expression the definite integral of f of x from x equals a to x equals b. And our notation is going to look like this. Which should look very familiar from the end of chapter 4. So before, when we didn't have the a and the b stuck to that integral sign, we called this the indefinite integral, and it essentially just meant to find the antiderivative. And this does have a lot to do with that antiderivative, but it takes that antiderivative one step further and makes a calculation. So when we put the a and the b on there, what we're going to call the limits of the integral, this is going to have some sort of meaning. For us, it's going to be area. I mentioned there's lots of other things this can calculate. So we're going to call this a and the b the limits. The a will be the lower limit, and the b will be the upper limit. And of course, this does have a connection with those antiderivatives, and we're going to get into that whenever we get into section 5.3. For the rest of this video, we're going to focus on the area meaning of this definite integral and a couple of quirks that come along with it. So this definite integral I mentioned has a couple of quirks, and we're going to get to the first one here. The definite integral of f of x from a to b gives the exact area between f of x and the x-axis on an interval a to b. But because it does that using those rectangles and it uses y coordinates for the height, in any region where the function has negative y coordinates, where the function dips below the x-axis, this definite integral is going to report that area as being negative because it's getting a negative height from the function. So we're going to say it's the exact area, but that it calculates any area below the x-axis as negative. So we'll just have to keep that in mind. We know the area can't be negative, but that's what this definite integral is going to do for us. So I'm going to show you how to calculate these definite integrals using antiderivatives whenever we get to section 5.3. For now, we want to focus on the area meaning of these definite integrals. So here I have a function f of x, and we're going to evaluate the definite integral of f of x from x equals 0 to x equals 2. So again, we're going to think of that in terms of the area between the function and the x-axis from x equals 0 to x equals 2. So I'm just going to shade that area right now. So between the function and the x-axis, just between x equals 0 and x equals 2. So I don't need an antiderivative to be able to calculate the area of that blue region. That's just a triangle. I know the area of a triangle is 1/2 base times height. So we're going to say this is 1/2 base times height. The base of that triangle is those 2 x tick marks. So I have 1/2 times 2. The height of that rectangle is those 4 y tick marks. So times 4 The 1/2 and the 2 cancel out, so this is just equal to 4. So this is what we're going to do for the rest of the video, just kind of focus on the area meaning of that definite integral. Same function f of x, this time our definite integral is from x equals 2 to x equals 6. So let's shade that area. So the area between the function and the x-axis from x equals 2 to x equals 6. And again, I'm going to try to focus on doing this with an area equation. That looks like a semicircle. So we're going to use the fact that the area of a circle is pi r squared. I've only got a half of a circle here. So we're going to say this is 1/2 pi r squared. And let's see what the radius of our circle is. So the radius, here's the center, and the radius looks like it's just equal to 2 tick marks. So my area is going to be 1/2 pi times 2 squared. So that's 1/2 pi times 4. And then we'll just reduce the 4 and the 2. So I'm going to get 2 pi. And you might have noticed I'm leaving a little bit of a space between my calculation and the equal sign. This is because we have to remember the quirk of the definite integral, that any area that's located below the x-axis, because we're going to have negative y coordinates in that region, the definite integral is going to report this as negative area. So your answer for your definite integral here is a negative value. We know that the area is a positive 2 pi, but the definite integral from 2 to 6 is equal to negative 2 pi. All right, same function. Now we're going to calculate the definite integral from x equals 0 to x equals 7. So this is all the way from the y-axis to the end of the graph that we can see here. We've already calculated some of this. We calculated the integral from 0 to 2. We colored that one in blue. We did 1/2 base times height. We got that area to be equal to 4. Then we calculated the semicircular area down here. That one we got as a negative value because it's below the x-axis. So this is negative 2 pi. And then we have to go all the way to 7. So we've got a little bit of extra area that we haven't done yet. This is this area from 6 to 7. All right, so that's another triangle. So let's just use our 1/2 base times height. 1/2 base times height. And both the base and the height are equal to 1 this time. So we've got 1/2 1 times 1. So we've got 1/2. So our definite integral from 0 to 7 is going to lump all of these 3 areas together, the blue, the green, and the pink. So we're going to say we want that blue area, the negative green area, and then that positive pink area, which was 1/2. So 2 pi isn't going to combine easily with the other two, but I can make 4 and 1/2 combine together. So let's rewrite 4 as 8/2. So that I can combine that with the 1/2. So that's going to be 9/2. So I'm going to get 9/2 minus 2 pi. So if you were to take that 9/2 minus 2 pi onto your calculator and plug it in, you're going to get a negative number. And what that means is that the negative area below the x-axis is more than the pink and the blue areas above the x-axis combined. So definite integrals have a way of sort of canceling out areas that are above and below the x-axis. This is something that we need to keep in mind about the definite integral going forward.